Okay, we'll finish up today talking about injection methods and then detectors that are commonly used in CE. I think it helps if we're going to talk about injections. So CE injections to consider kind of the layout of or a schematic layout of the whole instrument. So here's your capillary where all this good stuff's happening. Somewhere on here we've said there's going to be an on-column detector. We'll talk about that a little bit later. You're going to have the inlet and the outlet of this capillary. So here's the capillary going into a vial of background electrolyte. Here's the capillary going into, or starting out at, this is the inlet, that's the outlet, starting out in a vial of background electrolyte. We're going to have electrodes in each of these vials, and between those electrodes is where we're going to apply this really high electric field that we've been talking about, so thousands of volts. Okay, so there's our power supply. And the thing we need to know for injection, so that's a decent schematic of basically everything that happens in the instrument. Actually kind of simple if you think about it compared to what we do to make HPLC work. To understand these injections, we have to know that we can trade out this inlet vial for another vial that contains sample. And so the practice of injecting basically involves swapping the inlet vial, doing something to get sample into the capillary, and then swapping the inlet vial back. So let's look at two common methods, or two common modes of injection in CE. The first one we call electrokinetic injections. So in electrokinetic injections, obviously we stop the electric field so that we're not, electrocuting ourselves or having poor electric field effects when there's no vial here. We stop the electric field, everything's stagnant, and the inlet is placed in the sample. And then we momentarily, and to be clear, this is sort of on the order of 1 to 10 seconds or so, depending on how much sample we're trying to get in there, we'll momentarily resume the E field. And once we've done that for 10 seconds or so, we'll stop, right? We'll stop the E field, right? We'll stop applying voltage so that we can replace the inlet in background electrolyte. And then we resume field application, the voltage application, and the separation happens. Okay, so the idea here is that during this portion of the injection, we have the sample at the inlet, and electrophoresis and electroosmosis is carrying all sorts of stuff, everything from the sample into the capillary a short ways. It only goes a short ways because we're only applying for a short time. We stop applying, we put background electrolyte back in, and that's how we get kind of the picture that we've talked about a few times already, which is a short sample plug with background electrolyte on either side. And as this field continues, the mixture components in this sample migrate at different velocities, and so at the end of the capillary, we'll get peaks out of that zone. Okay, so there's a pro to doing it this way, and that's that it's a pretty simple procedure. And it's easy to do with small sample volumes. And by small sample volumes, we're talking on the order of, if you have 1 microliter of total sample available to you in this vial, you can make a system like this work pretty easily. There's a big disadvantage to doing this. There's a big con, and that is that this injection is what we call a biased injection. So let's think about what that means. So if The physical mechanism during this step that carries sample into the capillary is electrophoresis and electroosmosis. It means that that move faster, right, as part of this separation mechanism, they go into the capillary. They're loaded into the capillary faster. And if they're loaded into the capillary faster for the same amount of time as things that are loaded into the capillary slower, you get more of them, right? So this biased injection favors analytes with high mu EPs. We're going to see representative peaks that don't represent what stuff looks like in the sample mixture, because the things that move faster will be overrepresented and the things that move slower will be underrepresented. There's, I guess, a second challenge here is that it becomes very difficult to determine or calculate the volume injected. We need to know all sorts of things about electroosmotic flow velocity and even electrophoretic mobility of every analyte to understand how much of each were injected. And so this becomes kind of a trial and error sort of thing if we want to understand some of the quantitative metrics there. So pretty much specifically to address this problem right here of the biased injection, there is a second methodology. That second methodology is called so number 2 is called hydrodynamic injection. And in a hydrodynamic injection, we use pressure at the inlet, or sometimes vacuum at the outlet. To transport sample into the capillary, to transport that sample mixture into the capillary. And actually, there's a really simple method for doing this. One of the things about CE, the instrumentation is so simple, people often build their own instruments. So they're commercial instruments, and those commercial instruments will use some kind of pressure source or some kind of vacuum source to get sample in there. If you build this thing on the benchtop yourself and you just have a piece of capillary, there's a really simple way to get pressure at the inlet, and that is to use gravity siphoning. And this is literally, you just lift the inlet, and this is while the inlet's submerged in the sample, you lift that sample and inlet above the outlet. And what will happen is, because the outlet is at a lower level, there'll be a pressure differential. So that causes a pressure difference between the inlet and outlet, and that causes things to flow downhill. So a little bit of sample flows into the capillary, right? So flow downhill. Okay, so that's the simple way of getting a hydrodynamic injection. Flow rates are generally a lot slower, so those injections last a lot longer than if you can apply high pressure at the inlet. So there's a pro to doing it this way. And obviously that pro is this is not biased. You're going to get sample into the capillary that represents the relative amounts of stuff that is in your initial sample. It's also very simple to calculate injected volume. We would do that with the Poiseuille equation, which I can never spell. There we go. Poiseuille equation, which we learned earlier in the semester. If we know the pressure, we know the capillary dimensions, we know how long we applied that pressure, we can get a volumetric flow rate times that amount of time will give us a volume that we injected into the capillary. There is a con to doing this. So I just said there's a very simple way of doing this, and that's true. If you're using an instrument to do this, you're going to have actual built-in instrumentation that produces a pressure at the inlet or a vacuum at the outlet. And it turns out that instrumentation can be problematic. And that's because you need, if you're going to have a nice reproducible inlet pressure or outlet vacuum, you need a perfect pressure seal with the vial that is also taking a capillary into it and also taking an electrode into it. There are tricky pressure connections made at those vials. So the big con here I'm going to say is that it can require what I like to call tricky instrumentation. It's not particularly complex, but it's instrumentation that can be finicky. Those pressure seals can be difficult to make perfectly. Another thing is that, of course, pressure-driven flow is parabolic, and so that momentary parabolic flow adds to band broadening. It makes it deteriorates your peak efficiency, your number of theoretical plates. But in general, these two methodologies, either going by electrokinetic or hydrodynamic injection, are the ways that we put a little bit of sample, a little plug or a zone of sample into the capillary. And I hope you can see, it's a lot simpler and requires a lot less instrumentation and honestly a lot less forethought than the design of injection schemes for HPLC, where you're trying to keep high pressures and not break high pressures, for example. Okay, the next topic we're going to talk about today, the last topic we're going to talk about today, are CE detectors. And we don't need to do too deep of a dive here because the detection technologies we're going to talk about are the same ones that we talked about in HPLC. And so they have some of the same properties, and we're not going to do a deep dive. What we're going to look at are the intricacies of some of these detection methods that are specific to CE. So here's the first thing you should know. A lot of people view detection as the biggest challenge. In CE. We agree with that. In my lab, we focus, actually a big part of our research program is on developing detection modes for CE. And to understand this, we just have to think about kind of an order of magnitude of how much stuff we're trying to measure compared to something like HPLC, right? So total capillary volume is on the order of 1 microliter. 1 microliter, depending on where you're coming from, that might sound like a lot or a little a sample. To us, to me, in my lab, it sounds like a lot. To most people, it sounds like a little. But remember, the issue here is that we're not filling the capillary with sample. We're putting a very small injection plug into that total volume of 1 microliter. That means that our typical injected volume is on the order of 1 nanoliter, 1/1000th of that. It can be 10 nanoliters, it can be up to 100 nanoliters, but this is a pretty typical value. So what does that mean? Well, if we have 1 nanoliter of sample and we want to detect in that 1 nanoliter sample something at a concentration of 1 micromolar, that means we need a detection methodology, a mode, an instrument for detecting that can measure 1 femtomole of sample. Doesn't sound like a lot, right? What if we get all the way down to 1 nanoliter of sample and we want to detect something with 1 nanomolar concentration? That is 1 attomole. That is a ridiculously small amount of sample. If I'm doing this right, I'm doing this in my head, but I think that's about 600 molecules. We need a detection method that can measure on the order of hundreds of molecules at a time, which is not a lot at all. Okay, so, and remember, obviously, that if we want to get good quantitative values in this area, this isn't our limit of detection. This is our LOQ, and our LOQ is somewhere on the order of 10 times our LOD. In other words, our LOD needs to be 10 times smaller than that. We need to be able to measure, we need to be able to detect on the order of tens of molecules in this scenario to be able to get a nice quantitative measurement at the nanomolar concentration. Okay, for this reason, I'm just going to add this as a note on this page so we don't have to start a new page. For this reason, because we're working with such small numbers of molecules, we generally rely on concentration-sensitive detection. So concentration-sensitive detection is kind of our go-to tool for getting at really low amounts. And that's because if we can couple that concentration-sensitive detection method to the really small volumes we're talking about, well, then these concentrations are not necessarily all that challenging. Okay, let's look at 4 different detection modes in CE. So the first one is UV vis detection. Same UV vis absorbance detection that we talked about in HPLC. And so here's what this would look like. You'd have some kind of broadband light source. I'll draw it as a light bulb. Um, it's putting out light of many wavelengths. You're going to couple that light via a lens with a very small focal distance. So this is a ball lens. It's literally what it sounds like. It's a sphere of glass. It's going to bend that light at a pretty sharp angle so that it can all intersect with the capillary. So this is the capillary coming out of the plane of the paper. There's our fluid, like the inner diameter where fluid can reside. And that will all become incident on some kind of detector. You'll remember from our discussion of UV vis absorbance in HPLC, we need some kind of wavelength selection. So either there's a monochromator on this side or there's a monochromator on this side. Or if we're working on one wavelength at a time, we'll just use filters. But this is the general idea. We use some kind of focusing optic to couple to these very, very small dimensions and small volumes inside the capillary. So here's the big challenge with this. UV vis absorbance is governed by Beer's law. So our signal absorbance is equal to, and I'm hoping this is review for everybody from undergrad um, analytical chemistry, it's equal to epsilon BC. So this is our signal absorbance is equal to this molar absorptivity constant, property of the molecule, the concentration, which is just something we're trying to determine, and this is the sticky wicket. This is where it becomes tricky. This is the path length. And you'll recall that we said these capillaries, so you can see how this is designed right here. Our path length is the width of this capillary, right? So the path length is always, because our capillaries are always so small, this is always 100 microns or less, right? It's whatever dimension of capillary we're using. For that reason, we don't get great concentration limits of detection here. So we can get LODs on the order of about 1 micromolar, and that's pushing it by UV vis absorbance. So if we want to get better sensitivity than this, we need something that is not path length dependent. That brings us to number 2, fluorescence detection. And what's super common here is laser induced fluorescence. And there's some controversy over whether this is actually different than regular fluorescence or not. I won't touch on that controversy. I'll just tell you that the definition of laser-induced fluorescence is fluorescence excited by a laser instead of by a broadband light source. And so here's what that would look like. Here's a laser. Here is your capillary. You're again going to use some kind of focusing optic to take light coming out of your laser and focus it down onto your capillary. That's going to excite fluorescence on molecules that are in that volume. They're going to emit light, and at 90 degrees here, we're going to try and collect that light with a lens. So this is a lens. We're going to try and collect that light with another lens. We need to make sure that the only light we're seeing, so scatter is a big problem here. So this laser light will bounce around and it'll end up going this way. And it'll be much brighter than the light that the molecules are emitting. And so we need to make sure that the only light we're detecting is the light that is being emitted. That fortunately has a different wavelength. So we use a filter here. So this emitted light is then focused through a filter onto some kind of detector, a PMT or an APD or something. Okay, so the beauty here is that this is not path length dependent. And I will leave the equations for sensitivity and fluorescence to a spectroscopy course, but you can look through. Basically, it is it's related to the fact that every molecule in here has the ability to excite and fluoresce many times over the course of its time in the detection volume, and so it's not path length dependent. And therefore, we can get to LODs, very good LODs here, actually. LODs on the order of picomolar. Picomolar limits of detection times, oh, it's not on this sheet, but picomolar limits of detection times nanoliter volumes of sample is pushing on the order of single molecule detection. Now, it's really hard to do that. And the other thing you have to realize is that this requires fluorescent samples, right? Everything doesn't fluoresce. And so we go through routines like we talked about in HPLC for fluorescently labeling samples, that kind of thing. But in the right circumstances, you can get really exquisite detection limits pushing single molecule detection, which is the ultimate in a detection limit. Okay, let's look at two more methodologies that are common for detection in CE, and then we will be all set. So let's call this electrochemical detection. We talked about this also in HPLC, and the idea is basically your sample undergoes a redox reaction at some detector electrodes, right? The real trick here, the key challenge, we'll call it, is to decouple the electric fields. There's two electric fields involved here, and we need them to not influence each other. The electric fields for CE and for the electrochemical detection, right, for the detection. So we need basically detection to not be influenced by the CE field. We need CE not to be influenced by the detection field. Here's the way this is typically done. Here's a capillary, and we are going to put the capillary ending in some kind of electrochemical detection cell. So here's a couple of electrodes. Let's suppose we apply plus voltage and minus voltage here. Maybe this is conductivity, maybe this is redox at these electrodes, but there's some kind of electrochemical process happening here. We're going to call this the detector cell. And because we're applying potential to make that happen, there's an electric field here. Of course, our separation needs an electric field, so we're going to apply plus high voltage here. And we need some way for this electric field to end before we get in there. And so the way this is done, so here's our high voltage application. So here's a battery schematic. So here's our plus high voltage going this way. Here's our minus high voltage or the other end of our field. And there's some region in the capillary where we get a small break or a porous region. Porous, there we go, region. Okay, so we have some porous region here in the capillary wall. This can be done by chemical etching. It can be done by a physical break in the capillary if you're very careful not to have that break open enough for everything to leak out. But the idea is we can apply that here, and so we get in the region between where we've applied the end of the CE field, we get some region here that is a field-free region. That means that this electric field never sees this electric field. That's the key challenge here. By these electrochemical methods, we can typically get limits of detection down to about 1 nanomolar. Maybe lower in some specialty cases. Okay, last detection mode shares in common this need to decouple the fields. The last would be mass spec. And we're not going to throw out any schematics or anything because, again, the key challenge here is doing the same thing, separating this, isolating or decoupling these two fields from each other. In this case, it's the CE field from not detector cell, but from what is most common. It would be the ESI ion source, right? We've seen ESI, the cone jet thing, apply a voltage, and you get droplets. So it's the same field decoupling problem to produce an ESI spray. So same field decoupling challenge, and it's tackled generally the same way. Right, so same field decoupling challenge. Here's where CE mass spec kind of has its biggest challenges, though. Mass spec is a mass-sensitive detection technique. We talked about that before for HPLC. And we've talked about really, really, really small amounts of sample, right? So small sample amounts. And another challenge, which is that CE requires that buffered constituent in here to drive our electric double layer, get our EOF, that kind of thing. Have nice stable pH for reproducible electrophoresis. So it has to be buffered. That requires high salt concentrations. And high salt concentrations really interfere with ionization by ESI. So small sample amounts, high salt concentrations, these are the key challenges in CE mass spec. Okay, so I think we've outlined a decent outline of detection modes and injection methods in CE. Next time we come back, we're going to talk about stuff that goes a little beyond these standard CE mechanisms that we've talked about. We're going to look at things like micellular electrokinetic chromatography and gel electrophoresis as different methods for getting more separation performance out of the electrophoresis method.